Hello everyone, we are Group 3 presenting our work on optimizing fast strategy for cycling. Prolonged or excessive stimulation during fast cycling can cause muscle fatigue, impacting therapy effectiveness. Our objective was to develop a system to detect and evaluate localized muscle fatigue, aiming to improve fast protocols for better outcomes. We used surface electromyography data, knowing its correlation with biochemical and physiological changes in muscle during contraction. Our analysis focused on frequency and time domain, expecting power spectrum shift toward lower frequencies and increased amplitude. For the SEMG data acquisition, we used TMSI system with 4 bipolar electrodes. As shown in the video, the subject was required to cycle for 10 minutes with a 5% resistance increase every 90 seconds. Moving on the signal processing, we divided each signals into intervals corresponding to the resistance increase, excluding initial and final segment to obtain stable portions of the signal. The study was based on 4 subjects that show similar results, but for simplicity we will show subject 2.
Shifting to the frequency domain analysis, we initially identified triggers in the overall signal. Then we calculated the average cadence across the entire range. Next, we selected pedals within a defined cadence range. And finally, we applied the fast Fourier transform for examining frequency component in individual pedal strokes. A standard signal processing was also performed in the time domain to prepare the data. In the fatigue detection strategy, the key index we've identified is the spectral centroid, computed as a weighted average of frequencies with weights corresponding to the spectral values at each bin. The resulting frequency indicated the central tendency of the signal frequency content. As expected from literature, our results show a decreasing trend in both rectus femoris muscles, more pronounced in the right one due to its extensive involvement in cycling. Additionally, we employed the median frequency, representing the frequency at which the EMG power spectrum divides into 2 regions with equal amplitude. This index, although it exhibits a relevant decreasing trend in most rectus femoris, it also shows a growth trend in some muscles, highlighting the index limited universal applicability.
In the time domain analysis, we focused on the mean amplitude value and root mean square, as shown in the slide, which are both indicators of the average signal amplitude. In literature, EMG amplitude has always been considered a controversial index, since its increase may be related to force increase rather than fatigue. To address this, we normalized the EMG signal using the mean force exerted on the pedals during each interval, resulting in a more robust index. The results we obtained were less reliable than the frequency indexes, but can still be taken into consideration. For potential real-time implementation, our approach involved using single pedal strikes to formulate predictions. We suggested acquiring baseline values by averaging indexes from initial strikes, along with the standard deviations. Then we compute the indexes for each strikes and measure their distance from the baseline. By comparing these values to a threshold, we assign a binary value to each index. The final fatigue estimate was calculated through a weighted sum of each index, with weights derived from experimental results. To obtain an even more robust estimate, we suggest verifying that fatigue is above threshold for a certain number of consecutive pedal strikes before sending an alert. We thank you for your attention.